Welcome back everyone. In this lecture we will actually talk about Serre's presentation of semi-simple Lie algebras. So with this lecture we will complete the course. Okay. So as before, so in the last lecture I actually told you about some relations that are satisfied in the semi-simple Lie algebra. So let us recall that. So if we take G to be semi-simple Lie algebra, so then you have, let us say, fix one carton inside G. So this is the carton of G. So then you have the root system and inside you have the set of simple roots. So you denote the elements of pi to be alpha 1 etc. alpha L. So where L is the rank of the Lie algebra, which is also the dimension of the carton. So now each this I from 1 to L, so we have this SL2 triple, SL2 I triple, so which is Xi, Hi and Yi, which we did, which is fixed. Okay. So with this what we proved that G is actually generated by these 3L generators, and these generators also satisfies some relations, and these 3L generators satisfy the following relations. So what are they? Again, first three relations are easy. So the elements Hi, Hj, so they commute, and the second relation, whenever you take Xi, Yj, so then you get delta Ij, chronicle delta Ij, Hi. The third relation, this tells about the action of Hi on Xj. So that is going to be given by alpha j alpha I, this kata number associated with this tuple on Xj. Similarly, on Yj it will act with minus, and the fourth and fifth relation, there are some important relations comes from SL2 theory. So these are called Serre relations. So if you apply add Xi minus alpha j alpha I times plus 1 on Xj, so then this will be 0. Similarly, if you apply same thing on Yi, Yj, add Yi power this many number of times plus 1 on Yj, so that is also 0. So these are called Serre relations. Okay. So we are going to actually tell that so this semi-simple Lie algebra is actually completely determined by, so these generators modulo these relations. So that indeed actually tells you that, okay, so how to construct the semi-simple Lie algebra from a given root system, because all important thing is the only data that we need to know is how many generators that we need. So given a root system, we have the carton matrix associated with that root system. So that is actually unique up to reordering. Okay. So then in particularly the dimension of that matrix, so that is L, so that is uniquely determined. Okay. So that L, once we know that 3L, so that means 3L generators we can pick, we can call them Xi, Hi, Yi, there is no issue. And then you can see that first two relations are easy to write down without any information about the root system. But the third relation and fourth and fifth involves some information about the set of roots. So for example, this alpha j alpha I, this kata number is what we need to write down this relation 3, 4 and 5. But that if you think about it, it is nothing but jith entry of your Cartan matrix. So, in particularly if you are interested in constructing semi-simple Lie algebra from the root system, okay, you start with the root system, then take the Cartan matrix associated with the root system. So, this is the Cartan matrix. So, we already seen that the Cartan matrix is unique up to reordering because Cartan matrix is defined from the set of simple roots, but all this set of simple roots, they are conjugate under the while group. Okay. So, you get unique Cartan matrix up to reordering. So, now given this Cartan matrix, you know the ijth entries. Okay. So, you can call them Cij. So, then if you are interested in reconstructing the Lie algebra, you plug in that Cji here. Okay. So, that way you will be able to reconstruct the semi-simple Lie algebra. But what is the meaning of that? So, that we have to make it precise mathematically. So, then we have to say what is some Lie algebra given by generators and relations. Okay. If we make sense of that, so then we can just take this to be the definition of our Lie algebra that we are interested in. Of course, it requires lots of work to prove that this Lie algebra that we are going to construct using the Cartan matrix is indeed even finite dimensional. Okay. We have to prove that. Once we prove it is finite dimensional, more or less that proof tells us that the corresponding Lie algebra will be semi-simple Lie algebra whose root system will be just isomorphic to phi. But anyway, that is really a big theorem that we are not going to prove, but I will just sketch how to construct the Lie algebra. So, for that purpose we need to actually define few things. So, to begin with, first we need what is called tensor algebra or free associative algebra. So, let us define that and then we will define slowly the other terminologies. So, the first terminology that we want is tensor algebra. The second one we want is free Lie algebra. So, then we can talk about presentation. So, that is generators and relations. So, this is something you must have seen in group theory. Okay. So, you must have seen what is the meaning of a presentation of a group. So, group is generated by some elements modulo some relations. Okay. So, the way you do in group theory, you start with the group G, you want to say that this group is generated by let us say some symbols xi modulo some relations rj. Okay. So, then what is the meaning of this? This means you take the free group generated by these xi's and then inside this you take the normal subgroup generated by rj. So, this is normal subgroup generated by rj's. So, if you take this quotient must be isomorphic to G. So, that is the meaning of this group is generated by some set of generators modulo some set of relations. Okay. So, in Lie algebra is also you want to define in a similar manner, but for that we need to understand what is free Lie algebra. Okay. So, but before that let us understand the tensor algebra which is indeed some kind of free associative algebra. So, let us start with the vector space. Okay. So, let us say V is a vector space over C and then we will have a basis. Okay. Call that basis xi. So, this is span of some xi where I coming from I. Now, what we want to do, so only things that we know about this exercise, we know how to add and then we know how to take scalar product among this exercise. Okay. So, it makes sense to write down the linear combination alpha 1 x1 plus etc. plus alpha n xn. So, this makes sense where xi's are coming from this basis. But we do not know how to multiply them, this x1, x2, how to multiply, that is something we do not know. But most of the time it is important to actually look at the associative algebra that can generate. Okay. So, that is a very important concept. So, for that purpose, so if we can actually construct some associative algebra that contains V, and then this V freely generates that associative algebra, that is more or less serves our purpose. Okay. So, that is why we just implement that we will be able to take product between xi's without any relations. So, that is all we are doing in order to construct this free associative algebra generated by xi. Okay. What we are interested in? We are interested in constructing free associative algebra generated by these xi's, okay, or by capital V. But how one does this? Okay. So, we have to take products of these xi's. So, that somewhat we have to give meaning. So, we have to give meaning to the product xi1 etc. xir. So, if we give meaning, then we can take linear combination of this. Since associativity is there, it does not matter how we write this product. So, the brackets really do not matter for us. Okay. So, in particularly I can take linear combination of this, and then we can actually we can treat them as monomial, and then if given two monomial, if we tell that how we actually take product between them, so that will be the obvious product, that is called juxtaposition, then we are in the business, we constructed the free associative algebra. Okay. But this is very kind of rough idea, but mathematically if you are interested in constructing this, then that is done using what is called tensor products. Okay. So, let us see that definition. Okay. So, we have V. So, this is the vector space, and this also has this basis xi I in I. Okay. So, now what we are going to do, we will take this tensor products of V. Okay. For example, we take the zeroth product to be just the complex numbers, and the first tensor product to be first tensor power to be just V, and then the second tensor power to be just V tensor V. So, similarly one can define for any k. So, the kth tensor is defined to be the tensor product of k number of copies of V. Okay. So, if you do not know what is tensor product, I will urge you to actually recall this definition. The best reference will be Dumitton-Foote. Okay. So, you can look at abstract algebra by Dumitton-Foote. So, this is a famous book on abstract algebra. Once we have this k tensor, then there is a natural map from, if we take TKV and then TK dash V. Okay. From the product of these two, this k plus k dash V. So, note that this is given by, okay, on simple tensors. So, given by on simple tensors. So, what is simple tensor? Simple tensors actually span any k product. Okay. If I take this k tensor product, V tensor etc. tensor V, so it is easy to see that the span of this V1 tensor etc. Vk, where Vi comes from capital V, is actually spans this k tensor product of V. So, these elements are called simple tensors. One can also restrict to the basis of capital V and then take simple tensors among them. So, that will be enough to span this tensor product. Okay. I will leave it to you to think about it, but anyway, this natural map. So, there exists this natural map. So, that map is from this product of these two spaces to this k plus k dash degree space. So, it is given by on simple tensors. So, you take V1 tensor etc tensor Vk, and then W1 tensor etc Wk dash. So, this pair is mapped to, so as usual the juxtaposition of this. So, you take V1 tensor etc Vk, then tensor W1 tensor etc Wk dash. Okay. So, this is how this natural map, bilinear map behaved. So, it is this is bilinear, that means bilinear in each variable. Okay. So, now using this map one can actually talk about product, okay, because the product is actually just a bilinear map from T of V to T of V, okay, T of V cross T of V to T of V. So, these maps, all these maps that we have here, that extends to a multiplication on T of V. Okay. So, that gives T of V a structure of associative algebra. So, if you have not done this, if you have not seen this tensor algebra, I urge you to actually go back and then check all the details about this. This is not something I am doing in this course. So, T of V is an associative algebra, obviously generated by T1V, which is exactly isomorphic to V. So, V sits inside T of V as we identify V with T1V. Okay. And if you think about it, there is a natural way of defining this using commutative diagrams or universal properties. Okay. What is that property? If I start with A, which is an associative algebra, okay. So, maybe we can actually make it as unital because T0 V is complex numbers. It also happens that this becomes unital, okay, but that is not important. So, if you start with an associative algebra A, and then if you have a linear map from V to this capital A, then you can, there is this natural embedding of V to T of V, which we call it iota. So, if we call this map as F, this is just a linear map as a vector space. So, then there exists unique extension of this F to T of V, which we call it F tilde, so that this diagram commutes. Okay. So, given this pair, okay, capital A and F, there exists this F tilde from T of V to A such that this diagram commutes. Okay. So, that is the universal property of this tensor algebra T of V. So, this is called tensor algebra. So, now if you think about, if you take A to be unital, so that means there is an identity element of with respect to the multiplication, then there is this identity element here in T of V, which is that corresponding to the scalar 1 inside this T0 V. So, this 1 should map to the identity element here or the unit element in capital A. So, that is again like all somewhat covered in the basic algebra course. So, if you have not done this exercise, please do it. Okay. So, now it is not hard to see if we take this V to have the basis xi, where I is coming from capital I and this is a basis, let us say. So, then T of V will be spanned by all these elements xi1 etc xir, where I1 etc IR will come from capital I, where R will come from N, and there is this empty word that corresponds to 0. So, xi1 etc xir is the empty word 1 if R equal to 0. With this convention, we can see that this TV of V is spanned by all this. Here we identify this xi1 etc xir by xi1 tensor etc xir tensor. So this simple tensor is identified as xi1 etc xi. So we can just drop the tensor notation. It just means the juxtaposition here. So this is again very interesting fact. So this I also leave it as exercise. And indeed you can prove that this is actually a basis. So this is actually a basis of T of V. Okay. So all these are important things about this free associative algebra. So now if you go back to this universal property, this is what somewhat motivates us to define what is called free Lie algebra. If we think about it, if we are interested in the free Lie algebra, so what could be the free Lie algebra? Let us say generated by capital X. So capital X is given by subset xi, okay. Then first of all, what is the free associative algebra generated by this set X? Okay, let's see what it is. So the free associative algebra generated by this X, so that should definitely will have first of all the vector space structure. So all the linear combination of xi should be there, and then all possible product of xi should be there. So that means the best way to construct that, what we do, we take this free vector space spanned by this X, okay, take the free vector space spanned by capital X. So what is the meaning of this? This is treat capital elements of this capital X by X as basis of this Vx, that is all. So that means this is direct sum of Cxi where I comes from capital I. So this is, you treat this Xi to be basis. So if we construct this free vector space, so then you can take the tensor algebra corresponding to that. So that is the free associative algebra generated by this capital X. So now note that if you have a free associative algebra generated by capital X, then it is expected to have this following universal property. Any given map from capital X to some associative algebra, okay, so this is just a set map. This should be extended. So first of all, this X should sit inside T of X. So that is given by the iota, okay, because X is sitting inside Vx, Vx is sitting inside Tvx, okay. So that combination we call it iota. So then this given F, there exists unique F tilde such that this map is commutative, okay. So this universal property one expects to hold, because T of X is the largest associative algebra that is generated by capital X. That means there should not be any relations among elements of capital X, okay. That is why this property holding. Indeed, this is what motivates us to define free Lie algebra. So if you think about it, you take all possible monomials that comes from these elements of capital X and then take the span of that. So that is your free associative algebra. So if we want free Lie algebra generated by X, then what one should expect from this associative algebra construction? So this is the free Lie algebra generated by capital X. So free Lie algebra, first of all, it is a vector space. So combination of, like, linear combination of elements of X should be meaningful, okay. And then you also want like Lie products between them, okay. So the Lie products, the best way to denote it is just a bracket xi xj. But what will be the typical Lie monomials, okay. In associative algebra you have regular monomials, but if you think about in associative algebra, so x1, x2, x3, so this is same as, if you put the bracket here, then this is same as x1, x2, x3, okay, because it is associative. So that means instead of denoting it in two different notation, one can just use x1, x2, x3, that is the traditionally we do, that is what we do traditionally. But when we go to Lie algebra, it is not associative anymore, it is highly non-commutative, non-associative algebra. So, the order in which you take the product matters. Okay, if you change the order, the elements might change. So, that is why it is important to keep track of which order you are taking the product. So, for example, some monomial, like typical monomial, might look like this. So, this is called right normed word. Right normed Lie word. Okay. But again, if you think about it, this is not the only way to get Lie monomial. So, a typical, like more general Lie monomial, it will be right normed of right normed. If you call this as some x of I bar, then if you take x of I bar 1 and then bracket with x of I bar 2 and so on, x of I bar some k, and then bracket with x of I bar k plus 1. So, this will be the typical actually Lie monomial. So, because we need to keep track of the order, so this gets really ugly. Okay, you can see that this can be any length. So, it can become very ugly even for k equal to 1. So, this should have something like this xi 1 etc., some xi or xi r plus 1, and then it will have another bracket like this, some yj 1 etc., yjs, yjs plus 1 etc. So, then you can see that how ugly it gets, because we are keeping track of the order. But the thing is, it has to be a free Lie algebra. So, if you think about it, this whatever Lie algebra this is, this should have all the Lie monomials of this form, okay, and then span of them. Okay. So, is it enough? And not yeah, this is more or less should be enough, because it is a free, there should not be any relation. That means, if we take these Lie monomials, this should not become equal to 0, or any linear combination should not become 0. Okay. So, that is what free means. But how do you construct such things? Okay. So, here is the simplest way. So, if you think in terms of this universal property, so let me write down the universal property. So, then it actually kind of motivates us to what to do. So, you have x, let us say you have any map from x to g dash, where g dash is a Lie algebra. So, this x is just a set map, call it f. So, this is just set map. So, then from x to your free Lie algebra, you need to have a embedding, so that you call it iota again. Then given this f, you should have extension, unique extension, such that this commutes. Okay. Given g dash and f, there exists unique f tilde from fl of x to x, such that the following diagram commutes. So, what is the meaning of that? You first apply iota and then f tilde, then that should be equal to f. So, if this property is satisfied, then you can call this fl of x as universal object in this thing. So, that is free Lie algebra. Okay. So, how do you construct? The best way to do, so given this x, so because this g dash is actually a linear structure first of all. So, this is a vector space. So, we will be first able to extend this x to first the free vector space generated by x. Okay. So, then if you go there, then you can see that you will have a map from that Vx to this G dash. Then that map can be again extended to what is called this tensor algebra, provided this G dash sits inside some universal object. Okay. So, let's take that as block box. Okay. So, let me define this here. In some sense, this is what motivates us to define at this point what is called the universal enveloping algebra. Okay. So, the universal enveloping algebra. So, what it is of G dash. So, given a Lie algebra G dash, okay. So, we want to talk about this universal enveloping algebra. So, that is nothing but, so this G dash is actually sitting inside some associative algebra U G dash, and this G dash is actually the image. Okay. Let us call it iota. This iota of G dash generates this universal enveloping algebra. So, later I will tell you how to construct this universal enveloping algebra, but for time being you take this as block box. Okay. There is a associative algebra, there is an associative algebra called UG dash, and there is a map I such that, so from G dash to this UG dash you have this linear map which is also Lie algebra homomorphism if you treat this UG dash as Lie algebra using the associative structure. So, then if you look at the image of this G dash as an associative algebra, so this generates as an associative algebra. Okay. So, now you can see that given x you can extend to Vx, now you can extend to Tvx. So, here you have G dash. So, from Vx to G dash you have a natural map such that this commutes. From G dash to UG dash again you have a natural map this I. So, if you combine them you can see that you have a map here. So, then because this Vx to G dash you have actually have a map, if you take this composition of this map, this F tilde, this is F. So, you take this I F tilde, this map. So, you can see that defines a map from Vx to UG dash which is an associative algebra. So, then there exists unique extension, okay, such that this diagram commutes. If you put them together you can see that from x to Tvx, okay. So, let me x to Tvx and x to UG dash, this diagram commutes. But now we are interested in only the Lie algebra. Na? So, then you can see that if we take the subalgebra, so you take FL of x to be the Lie subalgebra generated by x inside Tvx, you treat it as Lie algebra with respect to the associative structure. Okay. So, this is the Lie algebra comes from the associative structure. So, then it is clear that okay, this map kind of this map that you have, okay, again this map you can call it F tilde. So, you can see that you have x sitting inside Tvx and then you have G dash map F and then you have I here UG dash, then you have this F tilde such that this diagram commutes. So, now what we are saying, you restrict this F tilde to this FL of x, then one can prove that this actually maps inside UG dash. Okay. So, this since this is a Lie algebra homomorphism, Lie algebra homomorphism and x to and it is extension of F from x to G dash. Okay. So, you can see that this image, it will actually the image of f tilde, the image of x under f tilde will sit inside this iota of g dash. Okay. But it is actually a big theorem called PBW theorem. So, that tells us that this iota of g dash is indeed isomorphic to g dash. So, in particularly if you think about it, since g dash is actually a Lie algebra, so the image of this FL of x, this should lie inside this iota of g dash. Okay. So, in particularly this f tilde is going to give us a map from FL of x to this iota of g dash. So, from this if you pull back you get a map to g dash. So, this way you can see that this x to g dash and then this FL of x is there, na? This is the iota. So, there exists this unique f tilde such that this diagram comes. Okay. So, this way one can actually prove the existence of this free Lie algebra generated by x. What it is? By definition, it is just the Lie subalgebra generated by x inside this Lie algebra, which is bracket TVX. Okay. You take this as definition. So, in this definition, so to prove the universal property, we use the existence of this universal enveloping algebra of G dash. Okay. And it is a big theorem. The map that we have, this I is indeed injective map, okay, and that is a Lie algebra homomorphism. So, this PBW theorem that I am not going to prove in this course, okay, you can actually read it from Humphreys. But how do you construct the universal algebra? Let us see. The universal algebra, what you can do, you can take the tensor algebra of G dash, okay, because G dash is a vector space, okay. It makes sense to consider this TG dash. So, TG dash is actually a associative algebra, there is no issue. But the problem is, as an associative algebra, it is too big. So, if you take two elements of G dash, let us call it x and y. So, then the bracket of x y that is an element of G dash, okay, that makes sense. But the bracket of x y inside the associative algebra, you want to identify this with x y minus y x, okay. But if you look at this individual monomial x y, so these x y's they are inside T G dash, okay, but all we want is the bracket x y. So, that is even though it is in T G dash is actually becoming too big, because it also allows monomials of the form x y, which is not indeed like will not be there in the associative algebra generated by G dash, na. So, that is where the problem. So, for that purpose we have to cut down this T G dash. So, how do you cut down and then make another associative algebra? The best way to do is take the two sided ideal, just go modulo that. So, for that purpose what we do, we take this two sided ideal and then go modulo like this, take x y. So, all we want is x y minus y x, it should be identified with bracket x y. So, you take two sided ideal generated by x y minus y x minus x y, where x y comes from G, okay. So, that you denote it by u G dash. So, that is your universal enveloping algebra, okay. So, then you have a natural map from G dash to T G dash and then T G dash to this u G dash, that map you call it I. So, clearly this I is Lie algebra homomorphism. So, now I will leave it to you to check. So, here is this interesting exercise. So, this universal empire algebra is the biggest associative algebra that contains G dash as its Lie subalgebra. So, what I mean by that, if you have G dash to some associative algebra A, some Lie algebra homomorphism. So, now this F is Lie algebra homomorphism. You are thinking this capital A as Lie algebra using the associative structure. Then from G dash to UG dash you already have this I, which is Lie algebra homomorphism. So, then what is the universal property says, this F can be extended uniquely as F tilde such that this diagram commutes. Here this F tilde is actually an associative algebra homomorphism. So, it matches up the structure on the right side. Okay. So, this is the property of universal mapping algebra, and it is corollary of PBW theorem that this map that we have I from G dash to UG dash is an injective map. So, it requires really big proof, okay, which I am not going to do in this course. Okay. So, this is all general construction of free Lie algebra. So, now what is about presentation? So, if you have a free Lie algebra, let us say FL of x, then we can take some ideal inside that FL of x. So, that could be generated by some yj's. Okay. So, then this quotient is what, if it is your G, then we say that G is generated by xi I in I, where capital X is your set xi I in I, and modulo the relations yj equal to 0 where j is coming from capital J. Okay. So, this is exactly like in the group case, you have the free object on the top and then modulo some relations. Then if G is isomorphic to this, then you call G is generated by these xi's modulo these relations. Okay. So, now if we go back to our original question, so we can take we can take some root system phi, then you can fix a set of simple roots, and associated with that you can fix this Cartan matrix, okay, which is L by L matrix, where L is the rank of phi or the dimension of the Euclidean space E. Okay. So, this matrix if I have Cij, so then you can go back to this presentation of Serre presentation. You take this free Lie algebra generated by these 3 L generators xi, hi, yi, and then modulo you take go modulo the ideal generated by these relations. You replace this alpha j alpha I by C j I. So, everywhere you replace this by C j I, and here also you replace by C j I. So, then all you are doing, you take the free Lie algebra generated by this and then go modulo the ideal generated by these words. Okay. Instead of putting 0, you take this word and then take the ideal generated by that. Okay. So, that is you define to be your Lie algebra. So, basically you take FL of xi, yi, hi, where I range from 1 to L, and then you take ideal generated by hi, hj, and then xi, yj minus delta ij, hj, hi, and then hi, xj is cji, xj, hi, yj minus plus, this is I will write it as minus here, plus cji, yj, and then you take this xi, etc. xi xj, where minus cji plus 1 times xi appears, and then similarly take yi etc. yi yj, where yi appears again minus cji plus 1 times. So, I'll take all these elements, take the two side ideal generated by this and then go modulo this. You take this to be your Lie algebra. Then one can prove that this Lie algebra is indeed finite dimensional semi-simple Lie algebra, and the span of Hi that will form a basis that will form a Cartan subalgebra of G, and with respect to the adjoint action of that Cartan, you can talk about root space decomposition and set of roots. That set of roots, if you take the Cartan matrix of that, so that will be up to reordering will be equal to the Cartan matrix that we started with. So, then indeed it proves that given Dynkin diagram, okay, so we already seen that there is a unique way to determine the Cartan matrix. We also explained the algorithm. So, from that you can recover the Cartan matrix. From the Cartan matrix, now you can recover the semi-simple Lie algebra completely using the Serre presentation. So, this way that association that we talked about from G to its root system, that becomes actually bijective correspondence. So, this way actually one completely classifies the finite dimensional semi-simple Lie algebras. Okay, so I am running out of time, I will stop here. Okay, so with this actually I conclude the course. So, modulo the existence of this semi-simple Lie algebra using the Serre presentation. So, we have actually completely completed the classification of finite dimensional semi-simple Lie algebras with the help of the classification of finite root systems. So, thanks for your patience. I hope you must have enjoyed this course. Okay. So, we will see you some other place. Thank you very much.